Hello, welcome back. I'm back after a brief hiatus, initially to go to conference and then subsequently to recover from the COVID that I caught at the conference. Maybe conference is not a great idea right now, but it was kind of fun. It was nice to see people again. But I'm back for more learning Haskell online. The plan is to pick up from the last session I did. I kind of feel like a bit of a fraud. In the last session, I billed it as building a simple stack machine. And in the end, I didn't. I spent most of the time setting up a new project and playing with megaparsec to parse some input. So to make up for that, today I will also not be building a simple stack machine. I need to do a little bit more prep work before that. Specifically, I need to convert my input tokens into reverse Polish notation, which roughly means floating the operators to the end of the input stream, and the lower precedent stuff further out. I'm going to do that using Dijkstra's shunting yard algorithm, which is not a thing I know off by heart. It's a thing that I've looked up in preparation for this, although it was a couple of weeks ago. I hope I can still remember how to do it. It's not particularly complicated, but it'll probably take me an hour or so to get it working properly. So let's just have a quick look at what we had before. So we have this test where we take some input string and we turn it into a list of tokens. And then what we want to do tonight is convert this list of tokens into reverse Polish form by taking this and basically putting t plus at the end. That's what will happen here. And then for this more complicated thing, we'll float t mult to the outside and then t plus to the very end of that. I think in here, did I have? Yes, I have an example of the reverse Polish form of this expression. Just to make sure everything's still working, I'm going to make font a bit bigger. Let's zoom in a bit. I'm just going to make sure the tests still run. It says one of one test case has passed. That's good. Okay. Let me just copy that for a second. I don't need all of it, but I need the spec bit. I'm going to create a new test. I'm going to call it shunt spec. Just paste that in, and we will rename this to shunt spec. We'll import something in a minute. I will import the tokens though. Okay. What's it complaining about here? Sorry. Oh, sorry, I haven't imported collect parser, so there's not to do. Okay. So we say it converts the input to reverse Polish notation, and we won't call this calc parser. Let's just call it shunt, and we'll give it a list of input tokens. Something like that. And then we'll say it should parse. It doesn't parse here, right? That's the problem. So it should be. And then we will reorder this to be the correct form. T plus. Okay, so I need to do the right shunt, and then we should be good. I might as well write the next test case as well. Oh, don't do that. Let all tabs go away. Okay, so we're done. Right. So it's, let's say something like it handles multiple operators. So we will do, what was the example I had in the plan? It was plus and then times. Okay, so t mult, I think it was. Yep. And then t num 3, let's say. And here, I think it should be t_num3 and then t_mult and then t plus at the end. That's what we should end up with. And we just check that against the original plan. So it was, yeah, 1, 2, 3, mult, and then plus, and plus. Okay. So let's go and update Cabal first of all. So here we should be able to say shunt spec. And up here we will also have shunt, which I need to go and create. Okay. So in lib source, well, yeah, source, we can have shunt.hs. We can say module shunt, and we will export a function called shunt. I'll let the formatter format this. Where, and then we'll just say, so shunt will take a list of tokens and return a list of tokens, but reordered. And then she will say shunt is undefined. And then we will import, oh, it's not a token, what was it called? Tokens. And it's a calc token to avoid the namespace clashes. Okay, so we go back to here. I should be able to import shunt. No, I'm going to restart Cabal, restart HLS. Oh, why is this failing? Is it no longer failing? Let's try and run the test. The test should fail, right? Because it doesn't, it's undefined. Yeah. Okay. Get rid of that. Can I get rid of that? Yep. Just gonna write the wrong definition of shunt. So we'll just return the input that we got and just make sure the test fails in the way they expect. Yeah, it's good. So it's not reordering. Okay. So the implementation of shunt and the implementation of the shunting or algorithm in general. What we need are two stores along the way. We're going to walk through the input string and put it into one of two stores. So we will have one stack, which we'll use for temporary storage, and then one sequence, which we're going to use for output. Let me go back to that for a second. So the way this works, shunting yard. So we will have two things. We're going to have a thing called operators, and this is going to be a stack. And initially it's going to be empty. And then we will have output or instructions, what do we want to call it? And this is going to be a queue. But I'll use it, I think I'll use a data type called data sequence for this. But let's just write queue for now. We'll work out the actual type of this in a second. So importantly, stack is last in, first out. Last in, first out. And this is first in, first out. Okay, so our list of tokens, we got one, and then we got plus, and then oops, and then two. So we take each token in turn. We take the number one, and we can say this is a number. Therefore, we just add to output. Okay, so I don't know what, I just converted this to some weird format. Add the output, so now we can say that our output contains number 1. Very exciting. Then we get plus, which we can see is an operator. Therefore, we push onto operators. So now our operators just contain plus. Then we get to 2. This is a number. So the rule for a number is you just push the output or add to output. So we will end up with 1 and then 2. There is no more input. So no more input. What we do in this case is we pop from operators, and add to output, which means we pop plus and we add to output, which means our output now contains 1, 2, plus, which is exactly the thing we want. So for a slightly more complicated thing, 1 plus 2 times 3, it's almost the same. It's just we need to clarify what happens with operators a little bit. So first thing is easy, right? 1 is just add to output. So we end up with just 1 in the output. I'm going to show the two side by side. So I'm going to show operators and output. Then we get plus, and we say push onto operators. So now we end up with the operators containing plus and the output containing 1 as before. Not super exciting yet. 2, it's a number, so we add to output. So our operators contains this value of plus, and our output contains now 1 and then 2. Then times, right, I said we push into operators, but it's slightly more complicated than that. We push onto operators if lower precedence. So basically what we want to do, the full explanation of this is if higher precedence then top of operators, add to output, if lower precedence, pop until or maybe like while lower precedence, pop and add to output, otherwise push it. Okay, so what happens here is we hit the first rule. So the precedence of multiplication is higher than the precedence of plus. I'm saying higher here because it binds more tightly. I think that's the correct way around, which means that we add it to the output. So what we end up with in this case is we still end up with plus in our operators, and then we end up with 1 and then 2 and then times in our output. Okay, and now there's no more input. So pop, and this will empty out the our stack of operators, and then just add it to the end of our output. Okay, one final example to show you how this works, or to show me how this works, because I need to make sure I've got it right. So what we should end up with here is, what's the RPN of this? Well, I'll just follow the algorithm, see what we end up with. Okay, so first time through, we just push it, onto the output. Second thing is multiplication, so we add it to our operator stack. That's just the 1. Then we hit the 2, so we end up with this in our operator stack, and then 1 and 2 in our output. Then we hit the plus. Now the rule says if it's low precedence, while it's low precedencing in the operators, we pop from the operators and that's the output. And then push, sorry. Because we need to store this somewhere. So first thing we do is we pop from the operators. So we empty it, and then we just add it to the end of our output, and then we push onto the operator stack. So we end up with this, and then the next thing is a 3, so it doesn't affect the operators, but we end up with 1, 2, star 3. And then we're out of output, so we just pop off the operator stack and into the output. So we go 1, 2, star 3 plus. AB plus, plus. Okay. Okay. I might put this as a test case as well, just to make sure we get this answer out. I'm also going to manually evaluate this. I'm going to do that. Let's see. I don't know what all this nonsense is from before. Right. I'm gonna be a stack machine for a second. I'm going to be CPU. So my instruction set is 1, 2, star 3 plus, and my working stack is empty. So when we say a number, all we do is we take it off the instructions and we push it onto our stack, our working memory. We'll do the same thing for 2, so we should have a times 3 plus, oh goodness, plus, and we should have pushed it onto there, so it should let me 2 and 1. Then we did a multiplication. So multiplications is a binary operator, so we pop 2 things off, multiply them, and then push them. The 1 plus 2 times 3 example is missing the last stage of pushing the 3. 1 plus 2 plus 3. You are correct, sorry. I did forget to do the 3. Yep, let me come back and do that. Sorry, so that's 3 is add to output. I'm impressed people are watching and following along. So our output was 1, 2, and star, so it's now going to be 1, 2, star 3. And then there's no more output, so you get the 3 in there. Thank you. Is that right? That's not correct. Or is it correct? Hang on. 1 plus 2 times 3 should be 1, 2, 3 times plus. So maybe I've got my... That's what we're going to end up with. So maybe this rule is wrong. I could look it up. But let me... let me finish evaluating this manually. And then I'll come back. Because if I get the wrong answer, then I'll see if swapping the rules around fixes it. So I could have got the precedences the wrong way around. So what we've got here, sorry, I'm evaluating the multiplication, which means pop 2, do the operation and push it on. So 2 times 1 is just 2. So our remaining input is 3 and plus. And our output here is 2. Then we should get, we evaluate 3, so we just push that. So the only thing left is plus on there, and then it's 3 and then 2. And then when we evaluate plus, we pop 2, perform the operation and push it, so we should get 5. Which is the correct answer. But you should not get the same output for this. So what happened here? Plus was a lower precedence, so we ended up popping. And that gave me the right answer. For this one, multiplication is a higher precedence. I think this is wrong. Okay. It's probably just this. So it's not a lower precedence, which means that we end up just pushing it onto this list. Then we get 3. So we end up star plus on our operator list, and 1, 2, 3, and then no more input. So pop will give us this. So we take the first element off and we push it to the end of here. Okay, so yeah, thank you for pointing out missing the 3, because it also pointed out I got the rule incorrect. Right. Okay, so that seems to be the rule. When you get an operator, if you have an operator and it's lower precedence than the thing at the top of the stack, then you pop the thing off the top of the stack and you push it onto the output. And you do that until you hit that. You do that. You keep doing that while you have things of lower precedence. Otherwise, you just push it onto the stack. Okay, I'm going to take this example as well, I think, and put it in my test. Oops. Can I actually do multiple should be's? Let's find out. So this was T mult and T plus with the other way around. And we expected that to be 1, 2, T mult, 3, and then T plus. I've got multiple things, but it's only telling me about the first one. I don't know if I mean, it's right, separate cases for each of these things. Actually, it sounds like it handles precedence. And you should get 3 failures. Yep, Okay. Good, I think. So let me go back to here and we'll implement the algorithm that we had. So, first case, we have a tnum of some value, and then, oops, then we have some other tokens. I need to import tnum. And what do we say with that? Oh, we need a working memory. So we need the two things. So let me just say shunt is undefined for a second. I'll just put it back to ID for a second. So I'm going to write shunt prime. If I can find the correct key. So shunt prime has got a list of collect tokens. And it also has the current list of, it's got the stack. Let me just rename these things for a second. So it's got its stack, which is really just a list of collect tokens. And temporarily, I'm also just going to use a list for the output. And that's going to be collect token. So we got stack, we got output, and we got our final output. I'm not going to call this output because that's a bit confusing. Output is the final thing. Let's call this instructions. Okay, this is a bit better. Now we have our stack, we don't care what it is, and we have our instructions. So now we can say if it's a number, all we need to do is add it to the end of our instructions. But we're going to call shunt again. So we're going to call shunt again. This time the remaining tokens are t's, stack is unchanged, and the instructions are going to be, this is a little bit horrible, but it's going to be instructions, and we'll just put this on the end. It's a very inefficient way of doing this, but I'll come back to it. Okay. Oh, another case, right? So easy case, this one. You have the empty list, so there are no more input tokens. We don't care what, we do care what the stack is. And our instructions is pop all of S and I. So pop all is going to take the stack and the list of instructions, and it's going to produce a list of instructions. So pop all, I'm going to write this out in a long-winded way. There's probably a very easy way of doing this in Haskell, but I'll write it out verbosely and then just see if the language server can help me out. So first of all, if there's nothing in the stack, it's that. Otherwise, if we have x and x's and I, it's going to be pop all of x's And then we're adding this to the end again, so it's going to be I plus plus list containing X. Okay. What's the help? Use full all. Thank you. And then define what it use, we'll go back to that. What do we want? Which folder do we want? Probably data list. And what's the complaint work for I? It's shadowing an existing binding. Okay, it's not a great choice of variable names. Okay. My tab's not matching up. Let me just change this to be instructions. Don't know why it thinks it's not used. I don't know why it couldn't match. This is the error, isn't it? No? Oh, I don't know. Let me make them more. Make rid of the warning first so I can see the error. Okay, the other thing we have is if we have an operator, so it was T plus, I defined these as separate tokens, didn't I? That's going to be interesting. If it's T plus and then some other content and the stack and an I, it's going to be shunt. So T's, and then the stack, we just take our T plus and we add it to the beginning. And shunt of T mult and T's S and I is, now it gets a bit funkier. What I might do is just write a helper actually. So we're going to match some kind of operator here. And then we will call shunt operator. So we'll give it the op. An S and an I. What's that going to give me back? We can make this mutually recursive. So shunt operator, whoops. What's it going to take? It's going to take calc token, and it's going to take a stack. Oh, it's going to take an operator first. Sorry, it's going to take an operator and the stack and some instructions. It's going to return some instructions. I'm not super happy with that type signature actually. I'll come back to it later though. So shunt op is undefined. So the operator is going to be what might be a bit nicer. It would be quite nice if you get rid of all of the warnings. Okay. Right, so this needs to be tnum because it's a token that I'm adding onto the list. That's the first thing. And none of these things are used because I haven't used them. That's why they're not used. So this is going to be shunt prime, passing in tokens, and then just 2 empty lists. Okay. So anything I haven't dealt with is the operators. I'm not super enthused about this type of thing. I think what I'd like to say is S prime and I prime equal shunt op. Let me just give it the operator, the current stack and the current instructions in, and then we say shunt prime, we'll call it the remaining tokens, this new stack I got back, and the new set of instructions I got back. So now we can simplify this a little bit. So we're going to take some kind of token, which you know is an operator, some kind of stack, some kind of instructions, and we're going to return a stack instruction tuple. Okay, so now we can say we got our operator, we got our stack. So let's do some cases here. So if there's nothing in the stack, this is an easy thing, right? We just return the operator and I. So this is a case where the stack is currently empty. We don't need to think about anything, we just push it on. So otherwise, we will have something in the stack. This is like, I'm going to call them S and S's, awkwardly, and some list of instructions. And then we can use a guard. Use a guard. There we go, we can use a guard. Right, this is where the operator is lower precedence than S. Is that right? If operator is lower precedence than S, let me have a quick look at what we worked out before. If it's low precedence, then we pop the thing off. The thing we're pushing on is low precedence, we pop the thing off the stack. Okay, so we pop the thing off the stack, which is S, and we add it onto I. So we know our new instructions are going to be I plus S. That's partway there. And then we just recurse because we need to deal with everything else in the stack. So it's going to be shunt op, the operator, SS, and that. Let me just write lower precedence then. So it's going to take 2 tokens and it's going to return a bool. Lower precedence than. So if we've got T plus and T mult, it's true. lower precedence than otherwise is false. Okay. So if this is low precedence then the thing already on the list, then we pop the thing off the list and put it onto the end of our instructions, and we just keep going. Otherwise, we return. We push this onto the list of operators. So on that, and it's going to be push onto our list of operators. Oh, I should maybe capture that. Switch to the operators, and then we're going to also just turn the instructions. Right, I think that's the implementation. Super easy to read. I feel like I could have written this in a nicer way, but let's see what happens. Let's see if it works first. I'll be amazed if it works first time. I'm amazed it worked first time. Okay. Can we make this nicer? So the instructions are not great. We actually want to add to the end of it, and I want it to look up. So in containers, it's data.sequence, does it? Sequence is a doubly linked list, is that right? A finite sequence of values. Yeah, constant time access to both the front and the rear. So add an element to the left end and add to the right end. So I like the train jokes. Adding to the right end is adding to the end of the list, so I'm going to try and do that. So let's go to Cabal, and then everyone's going to break, obviously, because it hates me. In the library, we need to say build depends, and it's going to depend on containers, I think it is. It would have told me on this page somewhere. Containers 0651. So I can say, is it equals? I can't remember. 0.6.5.1. Let's see if that even compiles. I've got a lot of errors now. I may have fucked that up a little bit. Let me do that in any version. Let's see what happens. Will this restart and will it work? Yeah, I obviously fucked up the version specification. Okay, so I should now be able to say somehow this is a type right data sequence, and it starts off by being empty. So I'm hoping I can say import data.sequence. Okay, and then here we can say this is a sequence. Can we say that? No. Is it just called seq? Yes, I think it is. Okay. Is that the right type? It doesn't suggest that. No, it says here, data sequence of A. Right, okay. It's not quite enough. So it needs to be a sequence of calc tokens. And I presume it's got a to list, but maybe it doesn't. So constructors from list. Come on, other way. I don't scan sublist. Come on. I'm just going to assume it's got something called to list. And if it doesn't, we'll deal with that later. Okay, so initially this needs to be empty. And let's see if I can call to list on this. It seems to let me do that, so everything's great. Okay, so now our instructions, we should be able to say, what was it? That. To add to the end of it. I think all I need to do here is that. Avoid lambda. Right. Great. I guess that makes sense. What it's saying is run through from left to right, run through the stuff in X's, which is our stack, pop something off, and then run this with the accumulator. So take the current list of instructions and put it onto the end. Nice and easy. How many of these I got left? Oh, some I wanted. That's annoying. I'll just do one by one. Any more? Oh, that seems to be it. Okay, so same thing this time, super efficient using a sequence. Spec. Now recompiling it, and it still works. Okay, I don't know what to do because it worked. I'm really thrown. I expected to be spending lots of time at this point fixing up the code, but actually we now have some shunting. We could do a bit of an integration test. Yeah, let's try that just for fun. So as well as shunt spec, we can just say calc spec. Yep. We will export spec where spec has got type spec, and do that. Well, you can say spec is do it. Well, I guess it eventually is going to be it can add numbers, but we'll only do part of the process. So we can say calc. Then we have some input string, so we can say 1 plus 2. It should be, now eventually there should be 3, but for now let's just make sure we get as far as we can. So that's going to be tnum1, tnum2, and then t plus. Let's do that. We'll import that. We'll import this. And then we need to write calc. I'll do another test case just for fun, so it can add and multiply numbers. Oh, let's go multiply and add. So 1 times 2 plus 3. Oh, let's go crazy and go 9. That's incredible. So t num 9, then t mult, and then t plus. So we need to add calc. Calc source calc.hs. Calc will export a function called calc, and we can say calc is gonna take text, I think, and turn it into, temporarily we'll turn it into a list of calc tokens. So calc is going to be calc parse or something. I can't remember what the parser was called. Calc parser. Around, okay, it's going to be shunt after calc parser, basically. Let's do that. That. Couldn't match text with list of character. Okay, I do want it to be text, so we can do t to unpack. Can match type text with byte string. Unpack goes from byte string to word 8. Doesn't sound right, does it? But that doesn't work either, because that goes word 8 to byte string. Move string. That's interesting. So calc parser is not as easy as I thought. So couldn't match the either type. I was hoping to be like some kind of F map. Okay, I'm gonna have to do some more work, I think. So we got our tokens. We can say case that t's of, and then we can say left error. Oh, we could just maybe just do either. Something like that. And then what's... Oh, the type of this gets really complicated, doesn't it? So if we just call the parser, and for a second I'm going to make the type wrong and say void, and it says couldn't match that, and it's either parse error bundle string void. That's the bit I couldn't guess. Oops. So we can pull that in. Okay, cool. So now can we say, what's the function? It was shunt. So we can't do that, but can we do this? We cannot. We can do that. Okay, it just couldn't ever reduce it. I guess it makes sense. Can we write that instead? Okay. So we're going to go back to Cabal file and tell it about these things about it. So we now have calc, and we have calc spec. I call it calc spec. And import that. And this should be right. I won't worry about the error cases. Run that. And it didn't work. It didn't work because I got it wrong, I think. I think the answer is correct. So 1 times 2 plus 9. If I go back to my plan, it's 1 plus 2 times 9. So it is 1, 2 mult 9 plus. And I've written 1, 2, 9 mult plus. Okay. So the test is correct and I was wrong. Cool, that works. Okay, cool. So getting slightly closer. Eventually we end up with Calc being able to return the correct answer, but I can do that next week. There's a lot more stuff I can do that makes life a bit more complicated. So my shunting, actually let's go back to plan. My shunting doesn't deal with brackets properly. So brackets are a little bit more complicated. If I did, we had 1 plus 2 times 3, and that resulted in, what was it, 1, 2, 3 times plus. But if instead of that I had 1 plus 2 times 3, this changes the ordering. So what we should end up with, I think, is 1, 2 plus 3 times. And the way that works is when you hit the first bracket, you push it into your operator stack. And when you hit the second bracket, you pop all the stuff off. You basically pop until you hit balancing bracket. And then that introduces the idea that it might not find the balancing bracket, so you could have a syntax error. You could have that, which means that the type returned from shunt then becomes either error or instructions, and that just becomes a lot messier. So what I might do is not support brackets, implement the really simple stack machine next week or next time, and then come back to it and add brackets. And then maybe we can look at some more exciting stuff as well. I'm not running next week. I'm off on holiday, but the week after that, we should come back and finally write a stack machine, all being well. Cool. So thanks for watching. Thank you for train-related references and also pointing out the mistake I made. And yeah, see you in a couple of weeks, hopefully. Goodbye.